Hello, so I have to make a video for the Comp 272 lab that's due this week to prove we can make a 20-minute video and upload it to YouTube. So that's what this is. And we have to show we can record voice, so I'm also doing that. The lab is listed here. So from our team members, I'm a team member. I'll upload it to YouTube after, send it to the members, and then email it. It's not a very hard lab, nothing specific outside of that. You gotta show we can show voice, and so outside of this, I guess I will be talking about my Comp 255 project. You don't have to listen, it's just so I can ramble about something, I guess. Actually, I'll check one of the videos my group partner sent me. So here she sent this.
I will show the demo how for Hyper-V
Okay, I'll allow this to play.
monitor the virtual switch. Here is the demo environment I'm using. It's one cluster containing two Hyper-V servers. In each Hyper-V server, we have the virtual switch set up. And also we have several VLAN set up. One for management nodes, another for CSV, the cluster shared volume, and live migration. And there are several other virtual VLAN for virtual machine connections. And actually, for logical virtual switch, it can support NIC teaming. I can show more detail in the Hyper-V Manager and also the SCVMM. So right now, let's take a look on the Hyper-V Manager in one of my Hyper-V servers. So let's see, here's my remote desktop, and let's open the Hyper-V Manager. So we can see that there are two Hyper-V servers and all the virtual machine is running on there. This is more specific for operations, so it doesn't tell us too much information about the Hyper-V server and its performance metrics. And it has the virtual switch manager. However, it only tell the type of the virtual switch. It doesn't tell too much other information. So here we can see the type is external network. So that means it can connect to external network, and also the virtual machine can talk together and talk with the host of the Hyper-V server. And in order to see more detail of the virtual switch, I also we can go to the SCVMM console, and here's the SCVMM console. So if you open one of the Hyper-V server and go to the virtual switch, you will see that in here actually we are using the teaming. The logical switch actually support teaming in the new Hyper-V version, which means you can connect more than one physical adapter. They will work together as a single uplink. So here, my demo environment is server 01. It has a logical switch which connect to two physical adapters. So we can see that I jump a different administration console to see all those information here and there. So in Faultlight, actually, we can see all those components together, their performance metrics and dependence at the same time. So let's take a look at Faultlight Hyper-V monitoring and how it supports virtual switch monitor. Here is the Faultlight Hyper-V dashboard. So there are cluster. I have one cluster, and then all those performance metrics about the cluster and the performance metrics of each Hyper-V server, and also the virtual machine running on top of it. There's much more detail when you drill down to the Explorer view. But now I want to focus on the virtual switch, the new functionality I want to introduce. So if you click the virtual switch, you will see all those virtual switch performance metrics, and we list the top bandwidth, top network utilization, and also the packet loss, the highest number of ports, etc. And if you can go into individual virtual switch, for here we categorize into three different catalogs: external, internal, and private. So you can see individual virtual switch performance metrics, and here is the top virtual machine in terms of network throughput and also the packet loss. And also there will be dependence maps showing the network topology. Is things like that. It will be the virtual machine, virtual switch, and physical network adapter. So we can see the end-to-end visibility and all those performance metrics along the network topology. That is the for Hyper-V monitoring for virtual switch. Thanks.
Okay, so she sent me a 5-minute video and I was able to play that. I guess I'll go back to talking about CompE 255. So we had a data set from the police department of San Francisco that's available online, and we split it into multiple data sets based off the district it was in, and the data set is of police incidents. So anytime the police were called, it's logged into this data set. And so what we wanted to do is we wanted to create an algorithm that could predict the type of crime or incident happening, like assault or robbery or etc., based off the features that were around it. So like date, time, resolution, address, which is specific to the district, obviously. So I'll show you my work. So I did all my testing on the Bayview district. This is just importing a bunch of libraries. Oh, also we did it on multiple districts and on the overall city, so we could compare how our models perform. So the number of threads is 36. That's because I did all this stuff on an EC2 instance, and it had 36 virtual CPU cores. Model scores is just a list that I'm going to append every score for every different model type I tried. Random seed is just to set the random seed so I can regenerate it or reproduce the same result no matter how many times I run this. This is importing the CSV file, and we exported all the data into CSV files in a different script. Let's see if I can find that. Yeah, here it is. So we use Socrata from SodaPi, which is how they tell you to import it. We put everything into a CSV from there based off the district column name. So for example, for the whole city, we just put the whole data set in, and this encoding prevents us from having some weird errors that we were used to have. So for example, for Bayview, we're only doing it for the police district that's Bayview, and we're putting all of those into one data frame, which is of size 220,000 rows and 13 columns, which is a feature, 13 features. Send that each to a CSV. Did that for every district, basically. I think there's 10 districts total. Okay, so back to Bayview. I'm at about 8 minutes and 30 seconds, so I'll just keep explaining this. We read the CSV, get the shape 220,000 as I mentioned earlier. So printing all the columns, address, category, date, day of week, description, incident number, location, police department ID, resolution, time, X, and Y. So, and then this is the number of unique resolutions for my own testing purposes. And then here I dropped a bunch of columns, so these are unusable for features. So first one is police department district. This is just a random integer for their own tracking purposes. It won't have any effect on modeling and it won't be an important feature, so all it would do is mess with the modeling process. Incident number, same thing. It has no correlation to what type of crime occurred, so there's nothing involved that would be important. Police department ID is just, I think, the police officer ID, which also has nothing to do with it. Location, we drop location because we already have the X and Y longitude coordinates, and location is just X and Y concatenated, so don't need that. Description, we can't use description because what we're trying to do is categorize the crime based off the type of crime that occurred. So using description would be cheating, because if you don't know what type of crime occurred, you can't obviously know the description of it. So I print the shape again, same number of rows, except it has 5 less features because we dropped 5 features from our data frame. Printing them again. So category column that is right here. This is actually our Y, or our label that we're trying to predict. So I put that into a separate data frame, and I will drop Y a little further down. Yeah, right here. Labeling. Okay, so for this label encoder, this is to, because the model I'm using is XGBoost, which is extreme gradient boosting, and to do that, excuse me, you have to have all of the input features and the output label as numeric values. They can't be string categories, but they have to be numeric. So what label encoder does is it converts it's a library that converts string outputs or inputs or categories into numeric ones. So label encoder, after it converts it, it'll assume that all of the different types of whatever feature you just converted has a ordinal relationship, which means it'll look for some sort of way, or meaningful, how do I say this, meaningful reasons and differences and similarities between that feature. So if it's like a feature like, say, time, there is an ordinal relationship in time, because you go from 1 to 2. There's an ordinal relationship because you're moving forward an hour, and those 2 times are still similar to each other. Whereas for something like resolution, there's no ordinal relationship because they're all just separate resolutions. So like arresting someone or not arresting them, I don't know what all the resolutions were. I think I printed them. Yeah, arresting them or booking. There's no similarity between these. They're just random things. So I'll also have to one-hot encode those, which I will show later. These are to convert the date into a separate field, because date is year, month, and day, I think, in this format, and we convert them into 4 different fields for our purposes. And time, we want to, so originally time is as 24-hour clock, but it's an exact time, so like 22:35 or something. But we don't want that ending part. We want only 22, so that it'll be generic enough for the model or whatever modeling purpose we're using to find similarities, and so it's not so sparse. Okay, so I add day, month, year, hour into our data frame, and I can drop date and time now because I've separated this date obviously, and I've generalized the time. This is just showing what type of attribute each feature is. So since they're strings, I'm going to need to convert these into numeric values. Obviously, date, month, and year though are strings, but they're of integer type, so I can just simply do as type int. So that should leave us with just these 3 as strings: address, day of week, resolution. So the first thing I'll do is I'll label encode them. But as I mentioned earlier, if you just label encode them, then they'll assume they have some ordinal relationship between them. So what I'm also going to have to do is I'm going to have to one-hot encode them. And you don't have to. In this data set right here, I only did label encoding because you can assume there's some ordinal relationship and try and compare that to a different attempt where you do one-hot encode it, so you remove the ordinal relationship. So right here I did the one-hot encoding, and what one-hot encoding does is it, instead of converting them from strings, which label encoder does, to like 0, 1, 2, 3, 4, 5 as the categories, it'll convert it to multiple categories as binary things. So like if it's 0, it'll be all zeros. for however many category or different types there are. So there's, say, 3 resolutions, it'll be, or 4 resolutions, it'll be 0, 0, 0 or something, and then if it's 1, it'll be 0, 0, 0, 1 or whatever. Okay, alright, so here I put them all into columns and I append them and I stack them. This just creates a new array of our new features, basically. So I have address, day of week, and resolution at 1 hot encoded, and then X, Y, which are the longitude, latitude, day, month, year, hour as numeric, I believe, integers. So the shapes now. So for the 1 hot encoded one, since there's so many different addresses, it has to have so many columns, right, for each address, because they're binary now. It's not like an integer, like it's not just like 9 or something for the 9th address. It's 0, 0 or 1, 0, 0, 0 for a bunch of different columns. So that's why shape now has 3,800 columns. So if I just try and operate on this matrix of 3,800 features with 220,000 rows, there's no way I'll have enough memory allocation for this. So what I have to do is I have to convert this into a sparse matrix. This provides better memory computation during the things we're going to do. Sparse matrix, as I mentioned earlier, this is the item frequencies of each column. Pretty simple. Or of each label. So our Y, remember we label encoded it. So now instead of there being 39 types of different strings, there's 38 different categories for each type of category there is of crime. So like booked, arrest, or not booked, arrest, assault, robbery, etc., vandalism. So this is just listing the item frequencies of each of them for my own purposes. So I split it into a train and test set. The test size is 20%. I can use a small test size here because it's such a large data set, so it's not a huge difference. So here I apply XGB onto it. So what I'm doing is I'm doing cross-validation to find the optimal parameters, because XGB has so many different parameters. Number of estimators, which is number of trees it'll build. The learning rate, which, yeah, it's just learning rate of the tree. Max depth, how far the tree will go down. Cull sample is, so in order to avoid overfitting, which you have with tree-based models a lot, XGB allows you to do cull sample by level, I think, which is, it chooses, for each tree, it'll choose only a subset of the data, or cull sample by tree, which I'm using, which only uses a subsample of the features. So you'll avoid overfitting, because if you're not using every feature, you'll be able to find, you won't always use the same importance of features. So sometimes you'll have a less important feature trying something, or because the more important features won't be provided. So end thread, so as I mentioned earlier, 36 cores, so I'm using 36 cores for the XGB classifier. Only doing k-fold 3 splits because it's really computational heavy, so don't have the resources. Since I'm doing this on an EC2 instance, it costs money. I would have done it on the HPC, but from San Jose State, but I didn't have access to it in time. Shuffle is true because we don't want this data set to be the same all the time. You know, these parameters basically. I'm using randomized search TV instead of grid search TV to find the optimal parameters, because if you use grid search TV, this will take forever, probably 24 hours plus just for testing the baby set, because it'll make one for each combination. So 120.1, 0.2, 0.5, and then 120.1 to 0.4, whatever. What else was I gonna say? Well, I'm at 1930, so I just gotta finish this up. This is the execution of it. It didn't have great results, but that's because our provided features aren't that great, honestly, without description. 36 point, or 36% for the F1 score was our best result, which is decent, I guess, considering we're trying 39 different categories. And then I tried it again here, but this is with the one hot encoded. This is with the label encoded. This is with this is 35% was our best. This one I tried with the one hot encoded dataset, as well as using feature extraction at the start, which I used truncated SVD, just a form of PCA. And I'm just gonna cut it here because we're done.